morning, students. Last class we discussed about the Biot-Savart law and its application to find magnetic field about a circular loop. Right? Today in this class we are discussing a new law. It is Ampere's circuital law. We are discussing Ampere's circuital law and its applications. See, it states that the line integral of magnetic field of any circular loop about any current carrying wire is equal to a constant mu 0 times the current enclosed in the loop. That is, here is a current carrying wire. So there is a current in this direction. So we have taken a loop, a closed loop, imaginary loop around that current carrying wire. So this loop is of radius r. Of the loop we are taking a small elemental portion dl. So an elemental portion dl. So we are, when integrating over the length, it is line integral. This small portion of dl is the part of the entire loop. So if you are integrating this loop over the length dl, it is called a line integral. So line integral means integrating over the length about the magnetic field. So line integral of magnetic field, V magnetic field, this will develop magnetic field at that loop. So line integral of magnetic field over the entire closed loop. So we are integrating from length entire the loop. When we are finding such a line integral of magnetic field over the entire loop, it gives the value mu 0 into the current enclosed by that loop. See, the loop should be in a plane perpendicular to the direction of current. So in a loop which is perpendicular to the plane of current, the line integral of magnetic field about the loop is equal to mu 0 times the current enclosed. So line integral B dl equal to mu 0 I, where I is the current enclosed by the entire loop. This is Ampere's circuital theorem. Now we are applying this Ampere's circuital theorem to find the magnetic field about a straight current carrying wire. So we are having a straight current carrying wire of infinite length, and it carries a current of intensity I. The current flowing through that cross section, it is I. Now we are finding the first case, we are finding the magnetic field at a point outside the wire. So here, let the radius of this wire is A, and the distance which is where we are finding the magnetic field is outside, which is at a distance r. So here, as the point is outside, the distance to which we measure the magnetic field is very larger than the radius of this loop. So to determine the magnetic field, we have to select an Amperian loop. So a circular loop is taken with a radius of r. Okay. So by Ampere's circuital theorem, what we write? Closed line integral of magnetic field equal to mu 0 times the current is I. So B into closed line integral dl over the loop equal to mu 0 I. When we find the length integral, line integral of the entire length, it is what? The length integrating over the entire loop is the perimeter. So what we write? B into perimeter is 2 pi r. Integral over the entire loop of length is the perimeter of radius r. So B into 2 pi r equal to mu 0 I, or B equal to mu 0 I by 2 pi r. So at a point outside, the magnetic field is mu 0 I by 2 pi r. Now case 2, when the point is measured exactly on the conductor. So the point Q is selected, it is on the surface. On the surface. Now you can see the distance of the Amperian loop or the radius of the Ampere loop is equal to the radius of the conductor. The loop radius is as same as the radius of the conductor. So we are writing R equal to a point on the surface. So closed line integral B dl equal to mu 0 I, that is B into closed integral dl equal to mu 0 I, right? Or we can write B into, what is the perimeter of that loop? 2 pi into A, radius is A, mu 0 I. So we can write a point on the conductor B equal to mu 0 I by 2 pi A. So here R is equal to A, so B equal to mu 0 I by 2 pi A at a point on the surface. Alright, now let us take the cross section inside. So if it is inside, the third case, if at a point inside, we can take R is very less than the radius. The radius of the conductor is A, much less than which we are having a point inside. So at a point inside, the current of the cross section is different. For the entire cross section, the current is I. Now for the cross section which is taken inside the conductor, it carries a different current of I dash. So at a point inside the cross section, we write closed integral B dl equal to mu 0 into I dash, right? But here the current density, current per area is uniform. Current per area is very equal. So for the outer cross section, the current density is I by pi A square equal to, for the inner cross section, the current is I dash by pi R square. So we are writing I dash equal to I by A square into R square. So this I dash in terms of I can be written as I by A square into R square, right? So we are writing closed integral B dl equal to mu 0 into I by A square into R square. That is B into, what is line integral of B dl? It is B into 2 pi R equal to mu 0 I R square by A square. Here R and R square cancel. So B equal to mu 0 I by 2 pi A square into R. So at a point inside, we have B equal to mu 0 I by 2 pi A square into R. Now let us study the variation of magnetic field B about the straight wire with the distance from it. So when R is very greater than A, the point is outside, the equation we have B equal to mu 0 I by 2 pi R. So B is inversely proportional to R, point outside when R is very greater than A. At R equal to A, B equal to mu 0 I by 2 pi A. So this all are constant. Mu 0 by 2 pi is a constant, I is constant, A is constant. So B is a constant when the point is on the surface. But when the point is inside, we have the equation B equal to mu 0 I by 2 pi A square into R. So at a point inside, B is directly proportional to R. So we are plotting that here distance along the x-axis and the B value corresponds to along the y-axis. See, when this is the point where R equal to A, so there is a maximum value of magnetic field. But when R is very less than A, the point is inside where B directly proportional to A distance. So B and R is directly proportional at a point inside, and it is reaching the maximum when R, the distance of the loop is as same as distance of radius of the cross section. When we are increasing distance beyond that radius of cross section, the B and R is inversely related. So this is the plot of variation of magnetic field about this straight wire with distance from it using Ampere's circuital theorem. What is Ampere's circuital theorem? Line integral of magnetic field over an entire loop is equal to mu 0 times the current enclosed, provided the loop is in a plane perpendicular to the direction of current we are taken along the conductor.